few videos ago, we learned the definition of a prime number and a compound number. Now it's time for us to prove some of their properties. The first one is a proposition that says that every integer number, a, has a prime number that divides it. Before proving this proposition, let's look at this intuitive idea. If we have an integer a, then for a we have two options. A can be prime or not prime. If a is prime, then just set p equal to a, and then p divides a. But if a is not prime, then by definition there exists an integer v such that p divides a. Now for this integer v we again have two options. B can be prime or b can be not prime. Again, if b is prime, then just set p equal to b and p will divide a. And if b is not prime, then again we have that there exists an integer c such that c divides b. And so on until we get to a number that's not divisible by any other number, only itself and 1. Then that number would be a prime number and it would divide a. So it's clear once we've done this intuitive idea that we have to prove this proposition by induction. So let's go ahead and do that. Clearly it's enough to prove this proposition for any a positive greater than or equal to 2. And we're going to prove this by induction. So our assertion is going to be p of a. And p of a is going to say that there exists p prime such that p divides a. As we've seen in previous videos, every proof by induction has 3 steps. The basis steps are inductive hypothesis and then the inductive step. Let's start with the base case. As we're proving this for every a greater than or equal to 2, then the base case is when a equals 2, p of 2. And we have to ask ourselves if there exists an integer p prime such that p divides 2. And there does, because 2 is prime. And 2 divides 2. So just set p equal to 2 and the base case is true. Now our inductive hypothesis says that for every d that's between 1 and a, there exists a number p prime such that p divides d. And now it's time for us to do the inductive step. For this, let's take a greater than d. And as we did in the introduction, we have that a can have 2 options. A can be prime. In this case, p equal to a is prime and p divides a. Or a is not prime. Then there will exist a number b such that p divides a. But this number b is smaller than a. Then there exists a prime p such that p divides v. And if p divides v and v divides a, then p divides a. So we found a prime p such that p divides a. Then we have finished proving our proposition. Let's now try and prove this very important corollary. it says that the number of primes is infinite. The proof we're going to do is one that Euclid did in the year 300 before Christ. And it's not very hard. All we have to do is suppose we have a finite amount of positive primes. And let's say this number is n. Then the set of all primes is going to be p, and we're going to denote each prime as p sub 1, p2, and so on until we reach the last one, which is p sub n. Now let's consider this number, m, which is going to be the product of all the prime numbers plus 1. We can also write m as the product from I equal to 1 till n of p sub I plus 1. Well, we know that 2 is a prime number, then m will be greater than or equal to 2, because we're only considering the positive primes here. With our last proposition, there exists a prime number p such that p divides m. Now this p prime has to be on the list, so we're going to call it p sub I. Now p sub I divides m, and it also divides this product, p1 times p2 times pn. Then it will divide m minus this number, and it is pi divides 1. And this is a contradiction. Now the contradiction comes from supposing that this number was finite. Then we have a finite amount of prime numbers. Before moving on to our next theorem, let's look at a fundamental property of the prime numbers. If we have p prime and a any integer, then the greatest common divisor between p and a is going to be p if p divides a, and 1 if p does not divide a. So what this is telling us is that if p is co-prime with a, that is, the greatest common divisor between p and a is 1, then p does not divide a. But if p does not divide a, then the greatest common divisor between p and a is 1. So p and a will be co-prime. An important consequence of this is that if we have two integers a and b and a prime number p, and we know that p divides a times b, so what we have is that if p is co-prime with a, then p must divide b. This is because p being co-prime with a is equivalent to saying that p does not divide a. And if p was co-prime with p, then p would divide a. Because again, p being co-prime with p is equivalent to saying that p does not divide b. So this is very important because it's another definition of prime numbers. Instead of defining p prime if it has two divisors, itself and 1, we could say p is prime if and only if when p divides a times b, then p divides a or p divides b. It's another possible definition for prime numbers. Now we're gonna look at the last theorem in this video. the fundamental theorem of arithmetic. It's extremely important because it will show us why are mathematicians so eager to learn more about prime numbers and why are prime numbers considered the atoms in mathematics. This theorem is super old. It was actually used by Pythagoras in the 6th century before Christ, and its proof is by induction. So again, if you don't remember induction, I recommend you go back and check the first videos in the Algebra 1 reproduction list so you can understand this theorem fully. Now what the theorem says is that if we have an integer that's not 0 or plus or minus 1, then this number a can be represented in a exactly one way, apart from rearrangements, as a product of one or more primes. What this is telling us is that for every a, an integer, that's different from 0 and plus or minus 1, then there exists R, a natural number, and positive primes P1, P's of R, and natural numbers M1, MR, such that we can write A as plus or minus, depending on if A is positive or negative, P1, the first prime in our list, to the power M1, times P2 to the power M2, and so on until we get to the last prime in our list, PR to the power MR. These primes are all different from each other, and what I mean by saying apart from rearrangements is that we can also write A as plus or minus P2 to the power M2 times P1 to the power M1 times so on PR to the power MR, but these two representations will be considered the same because all we did was swap these two numbers, but the number they represent is the same. To prove this theorem, we have to pay attention to one thing. First, the can be represented. What this is telling us is existence, and in exactly one way it's telling us unicity. So we have to prove both these things to be able to prove the theorem. Let's start with existence. Like we did in other theorems, it's only necessary to prove it for an integer a that is greater than or equal to 2. And we'll be proving this by induction. And our assertion will be that a can be represented as a product of prime numbers. Let's start proving our base case. The base case is when a equals 2. P of 2 would be, can we write 2 as a product of prime numbers? Yes, because 2 equals 2 to the power 1. So we found 2 our prime number. Now, our inductive hypothesis is that if we had an integer d that's smaller than a, then P of d is true. So we can write d as a product of prime numbers. Now let's move on to our inductive step. What we have to do is first take an integer a. Now we have two options for a. The first one is that a is prime, and if a is prime, then a equals a to the power 1, and it's what we wanted to prove. And if A is not prime, then with the first proposition we saw in this video, we know there exists a P prime such that P divides A. Now, using the definition of divisibility, we know that there exists an integer k smaller than A, such that we can write A as k times P. But this k being smaller than A satisfies our inductive hypothesis. So P of k is true. So we know there exist prime numbers P1, PR, and natural numbers M1, MR, such that k equals the product of P1 to the power M1 and so on, PR to the power MR. Then A equals k times P, but k is P1 to the power M1, PR to the power MR times P. So we were able to write A as a product of prime numbers. Then P of A is true. And we were able to prove existence. Let's suppose our number A can be written as P1 to the power M1 times P2 to the power M2 and so on till PR to the power MR. But that it can also be written as Q1 to the power N1 times Q2 to the power N2 and so on until we get to Qk to the power Nk. What we want to see is that these two representations are the same. So we want to see that Pi equals Qj for some I and j. Let's first have a look at P1. We have that P1 to the power M1 multiplied by this big number is equal to this. So what we get is that P1 divides this number. Then, as P1 is prime, P1 must divide one of these, as we saw earlier in this video. So there exists, let's call it Qj to the power Nj, and P1 must divide it. So P1 divides Qj to the power Nj. And now we can write this as Qj times Qj and so on, Nj times. And again we have that P1 divides a product, and as P1 is prime, it must divide one of these elements, and they're all the same, so P1 divides Qj. But both P1 and Qj are primes. Then P1 is equal to Qj. And from here what we get is that M1 is equal to Nj. So what we can do is just divide on both sides by P1 to the power M1, and we'll get that P2 M2 times so on PR to the power MR is equal to Q1 to the power N1 so on the product until Qj minus 1 to the power Nj minus 1 times Qj plus 1 to the power Nj plus 1 and so on. We keep multiplying until we get to the last element, because qj was removed when we divided by p1 to the power m1, because p1 and qj are the same. But now we can repeat this process with p2. And so we get that for every I, a subindex that goes from 1 to r, there exists another subindex, j, that will go from 1 to k, such that pi equals qj, and mi will be equal to nj. And we were able to prove uniqueness because these two representations are the same. Let's finish this video showing a few examples of the fundamental theorem of arithmetics. If we take any number, we can always find prime numbers that will factorize it. For example, 15 is equal to 3 times 5. 3 and 5 are both primes. 84 equals 4 times 3 times 7, but 4 is not prime. Well, no problem, because 4 can be written as 2 squared times 3 times 7. If we get a more complicated number, like this one, then we can write it as 2 times 5 squared times 7 to the power 3 times 11. And you might think, well, multiplying these two numbers together is a very complicated task. But all you have to do is multiply their prime representations. So we have 2 times 2 squared, that equals 2 to the 3. Then you have 3 times nothing is just 3. Then you have 5 squared. Then you have 7 to the third, and 7 is 7 to the fourth. And the last one is 11. And we were able to find the prime representation of this number that is very complicated.